Hi, my name is Brian. Welcome to another video on derivatives. In this video, we are going to do another example using related rates. Recall that related rates is about differentiating implicit functions with respect to t. So let's go ahead and start with the word problem. A television camera is positioned 1,000 feet away from the base of a rocket launching pad. The angle of elevation of the camera has to change at the correct rate in order to keep the rocket in sight. Let's assume the rocket rises vertically at a speed of 500 feet per second when it has risen 2,000 feet in the air. So this question will have two parts. First part is how fast is the distance from the television camera to the rocket changing at that moment? And part B, if the television camera is always kept aimed at the rocket, how fast is the camera's angle of elevation changing at that moment? Okay, that was a very long word problem, so I'm going to actually move that out of the way. So step one and step two of solving related rates can be done at the same time. Step one is about writing down all the information you have and what it is you want. And step two is a snapshot, trying to draw a picture of what's happening at that moment. So let's go ahead and start with the picture. So we have a camera that is aimed at a rocket that is 1,000 feet from a launch pad. Now we have this rocket that takes off and is heading vertically at 500 feet per second. So this height right here is y, and we know that dy dt is going to be, what did I just say, 500 feet per second? All right, well, I ran out of room there, so I'll write that down here. So we know that dy dt is 500. And we know that it's positive 500 because y is increasing with time. And the first part of the question is about how fast is the distance from the camera to the rocket changing when the rocket is at 2,000 feet. Okay, so we want to know the speed of this line right here. So I'm going to have to call it something, so I'll call it z. And what I want is to find dz dt when y is 2,000 feet. Now what I have here is a right triangle, and I have my three sides. I need a formula, because this is part 3, a formula that relates my variable z and y together. So right now, since I just have the one triangle, I want to try Pythagorean's theorem to see if anything comes of it. So we have the 1,000 squared plus y squared is z squared. So here's the formula that's going to relate my variables together. The next step is to differentiate all sides. So we're going to take the derivative with respect to t. Oops, forgot that again. 1,000 squared plus y squared. All right, so when I differentiate the left-hand side, the derivative of 1,000 squared is just 0. And the derivative of y squared is going to be 2y. But since y is a function of t, we're going to have to multiply by the derivative of y, which is dy dt. If, again, you have any questions about how implicit differentiation works, we've got a bunch of other videos that go over that. On the right-hand side, we need to differentiate z squared, so that's going to be 2z. And again, since z is a function of time, we're going to have to multiply by the derivative of z, which is dz dt. Now there's the part I want. Okay. So I have dy dt. I know y right now because it's going to be at 2,000 feet. What I don't know is z, so we're going to have to figure that out. But right now, let's solve for dz dt since that's what I want. So I'm going to divide the 2z over, and so I'm going to get, the 2 is going to cancel, so I'm going to get y dy dt all over z. So like I said, we know y, I'll write this off here, we know y is 2,000, we know dy dt is 500, but I don't know z. So we have this rule that if you are setting up a related rate problem, you differentiate, and then you still have some variables without values, then go back to the original formula up here, and once you plug in all the variables, you should be able to find the missing one, which for us is z. So to find z, we have 1,000 squared plus, well, y, which is now 2,000 squared, is z squared. I need a calculator. Okay, got my hands on a calculator here. So we're going to have 1,000 squared plus 2,000 squared. Okay, so that's going to be 5 million. That's going to be 5 million here. And then we will square root both sides. And we get 2,236 and 0, I guess 7. We'll round to 2 decimals. So there's our third value. So let's go ahead and plug that in now. Y is 2,000. dy dt is 500. And z is going to be 2236.07. So that's our dz dt. So let me grab a calculator. 2,000 times 500 divided by 2236.07. And we get 447.21 feet per second. So that answer is how fast the rocket is moving away from the camera. Anyways, that's it for this video. I hope it helps. We're going to do part B in another video, so go check that out. Again, that's about how fast is the angle of this camera increasing as the rocket goes up. All right, see you in the next video. Bye.